Stanford University.
Let's begin. I'm going to begin with my interests. And this is very rapidly going to get into what I'm interested in and what I've been working on. But let's talk in a little bit of generalities first. The subject is quantum mechanics, and the subject is gravity and the relationship between them. Offhand, it sounds like maybe there isn't much relationship between them. Gravity is about the biggest things in the world, the biggest and heaviest things in the world. Oh, I see a whole bunch of people coming in. All right, I'll wait a second. I don't have my glasses on, but I think I recognize it. Is that Bartek? Hi, Bartek. He's one of our most important members of SITP, I would say. Also very young. Right. Offhand, you might think gravity doesn't have much to do with quantum mechanics. Quantum mechanics is about the very small and the very light, that which is so delicate that when you touch it, it does something, it jumps around and does all sorts of things because it's so small and so light. And gravity is about exactly the opposite, things which are so big and so heavy that in a sense they're the biggest and heaviest things that physics is about. And so what do they have to do with each other? Not much, you might think, but they come together in one special place. Black holes. Black holes are both highly quantum mechanical objects and, of course, highly gravitating objects. And that's the portal into the connection between quantum mechanics and gravity. Now, the essence of gravity is geometry. Geometry of space and time. The essence of quantum mechanics, well, various people would say there are different essences of quantum mechanics, but I think we're sort of converging over the years that the essence of quantum mechanics is entanglement. The strange difference between classical physics and quantum physics is largely encoded in the phenomena of entanglement. And another concept also that we will talk about, which is called computational complexity. These are the things I'm interested in, and what is happening is we're beginning to see the ideas of quantum mechanics be encoded in geometry in surprising ways that we never expected. The deepest principles of quantum mechanics, the strangeness of quantum mechanics, the weirdness of quantum mechanics, apparently what's happening is it's all being encoded and understood as aspects of geometry, particularly when the objects that we're studying quantum mechanically happen to be black holes. So that's what I'm going to tell you about largely. And as I said, there are lots of other people who have different thoughts than I do. They're all wrong, but that's, oh, they are. But, okay, so I'm going to begin with a concept that's called ER. Now, who can fill in the rest? There's at least 3 people in the audience that I know can fill in the rest, but I'll do it myself. Equals EPR. ER and EPR stand for names of people. And on the left-hand side, as you might expect, an E, what does E stand for? E stands for Einstein. Who else could it stand for? Einstein. On the right-hand side, E stands for Einstein. On the left-hand side, R stands for Rosen. You probably never heard of Rosen. He was a minor physicist who collaborated with Einstein, sort of one of his assistants. So the R's on both sides are the same. And the P in the middle is Podolsky, who was also a good physicist, but a relatively minor one. The ER on the left-hand side stands for a paper that was written by Einstein and Rosen in 1935, very much toward the end of Einstein's productive career. In fact, a lot of people up until recently would have said it had exceeded his time as an influential physicist. EPR stands for a fundamentally quantum mechanical idea, entanglement. Left-hand side, geometry, the geometry of black holes in particular. The right-hand side, a fundamental quantum concept of entanglement. And again, it stands for a paper that was written by Einstein, Podolsky, and Rosen in the same year, 1935. The two papers apparently had nothing to do with each other. This was usually credited as the paper which recognized the importance of entanglement or recognized the strangeness of entanglement. And the left-hand side had to do with black holes. It has turned out that they are so deeply related that one can almost put an equal sign between them, that they are so deeply connected, joined at the hip, the idea of Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement. So I'm going to tell you about that, and then I'm going to tell you, not tonight, I don't think, about a concept that is developing, or at least in my imagination it's developing, called computational complexity. The relationship, strangely, it's a relationship between concepts from computer science and concepts from quantum mechanics and gravity. So that's what this course is about. Okay, let's start with entanglement, though. Now, as I said, this course is for people who have the basics, who have learned, let me call it the theoretical minimum, and I am not going to spend time explaining things which I assume that an incoming graduate student who has had a good education in quantum mechanics and a good education in general relativity would be likely to know. That's the starting point. All right, so entanglement. Entanglement is a thing that can happen between systems, between pairs of systems. The simplest systems are qubits. A qubit is like a spin. It can either be up or down, or like a coin. It can be heads or tails. But a quantum mechanical version of it, which can be in superpositions of states. And if you have two qubits, the states are labeled either up or down. You can have an entangled superposition of them. This is an entangled superposition. One of them is up, the other one is down, minus, down, up. This is called a Bell pair, and it stands for the state of a two-qubit system. And it says, very simply, the two-qubit system is such that if the first qubit is up, the second one is definitely down. And if the first one is down, the first is up. There's a correlation between them. If you had these two entangled qubits, incidentally, they could be far apart. You could make the qubit pair and then take them far. Qubit stands for quantum bit. If you made the qubit pair, the bit of information as inside a computer, if you made the qubit pair, you could take them far apart from each other. And then, because of the structure of this state, you can say there's a correlation. If Bob over here measures his qubit and it's up, he knows instantly that Alice is down. This is Alice's qubit. If Bob's is down, then he knows that Alice is up. Now that in itself is not so weird. The way I usually like to describe this is I give one person a coin, which is a penny, the other person a coin, which is a dime. They don't know which is which, and I tell them to go out of the room. We never actually carry this out. The reason we never carry it out is because I never have a coin with me. Not having a coin, I feel perfectly free instead to do it with a $10,000 bill and a $1 bill. But this is all air money. I mean, I don't, so we have, here's a $10,000 bill. Art, you get one of them, and Sanjay gets another one. You don't have to stand up, I'll just pretend. Okay, so I mix them up. They're different. Real sugar and chemical sugar. And behind my back, and I give one to Art and one to Sanjay. I tell them to go out of the room. And then the amazing fact is the minute the second that Art opens up his package and discovers what it is, he knows instantly what Sanjay's is. How can that be? No, it doesn't seem very amazing, does it? It's just obvious. That's called correlation. Entanglement is a form of correlation, but in a moment I will tell you what the difference is. It's the state of being correlated for two coins or two bills is really got something to do with the fact that you didn't really know everything about the system that you could have known, that in principle could be known. In particular, somebody could have done a very, very delicate experiment without anybody even recognizing it. For example, by sending into the room a very, very, very low energy radio wave. A radio wave with maybe just a couple of quanta in it. And those quanta might bounce off the objects and record which one was which, without making any difference to the experiment. Classical mechanics is like that. You can measure things, you can look at them without changing them. You have a pair of coins, you can look at the coin without causing it to flip. Quantum mechanics is different. Quantum mechanics, when you look at something, you cause it to change. The peculiar thing about entanglement, the very, very strange thing about entanglement, is that knowing the quantum state in this form is everything that can possibly be known about those two qubits. There is no more to be known. A quantum state like this is the fullest possible description of the two qubits, and yet it says nothing whatever about what either one of them is doing. It is equally likely that the first qubit is up as that it is down. So it is a state of being which is absolutely the maximal you can know about the system, and yet you know nothing about the individual constituents. That sounds crazy from a classical viewpoint. From a classical viewpoint, if you know everything that there is to know about something, then you know everything there is to know about the parts of the system. An entangled state like this is a state in which you know everything about the system that can be known, and yet in this case you know nothing about either of the constituents. That's the notion of entanglement. Now, incidentally, for those who know about spin, you know you could measure the spin along other axes, not just up or down, but in and out or left and right. And it has the same property, that if Alice comes along and measures, instead of the upness or downness of this qubit, she measures the inness or outness of it, she will immediately know what Bob's qubit is doing in the same way, with respect to the same thing. She'll know that if she makes a measurement and this qubit is out, then Bob's is in. If this qubit is in, then Bob's is out. So it's something which is correlation, but it's a much more fundamental concept than just the statistical or just the fact that you may not have known which one of these I gave to Sanjay, which one I gave to Art. But somebody could have known, not with entanglement. So entangled states are very special, and they really do characterize in many ways what is quantum about quantum mechanics. Almost everything that's strange about quantum mechanics, that's really strange about it, things which are the really bizarre logic of it, traces back to entanglement. Now, can you make macroscopic objects which, there's another thing about, let me just say what it is. It has the property that you can find out any piece of information about what Alice is holding by making a measurement on what Bob is holding. This is the character of entanglement. You can find out everything you want to know, or anything you want, not everything, but anything you want to know about what Bob is holding, Alice can find out by measuring her own system, by doing an experiment on her own system. All right, are there macroscopic versions of this? Can you take large-scale objects and entangle them? Or can you create large-scale objects which are entangled in this way? Remember, they have the property that although you know everything about the combined system, you know nothing about its parts, or you cannot know anything about its parts, and you can find out anything about one of them by doing a measurement on the other one. Yes, you can. Here's how you can make a macroscopic system. First question is, how do you make entangled pairs like this? Well, there's an easy way. You just create particle pairs. You can create particle pairs, for example, electron-positron pairs in the laboratory by colliding photons together, all sorts of ways of doing it. When the electrons and the positrons come out, they are entangled. In fact, their spins are entangled in exactly this fashion. So you can easily create pairs of particles that live in this, that have this funny relationship between them. So you create a pair. The V here stands for the creation of the pair. One particle goes off one way, the other particle goes off the other way. Well, what do you have? You have two entangled particles separated from each other, and you put them in a box. And you put these in a box over here, too. And then you do it again. You create another entangled pair. And now this box has two particles. This box has two particles, and this one is entangled with this. You keep doing it. You keep doing it over and over and over again until you fill these boxes with large numbers of particles. There may be enough of them to create an interesting macroscopic object in each of these boxes, and those objects are fully entangled. They have this property that you can find out anything you want about one of them by doing a measurement on the other. So entanglement is not restricted to small objects. Large-scale objects can be entangled. Now, of course, where we're going is we're going to be talking about black holes. Any questions about entanglement? I would refer you to the lecture notes that I gave on entanglement, and there we are. Now, you might think in order to have entanglement, you have to have some particles. You have to have something to be entangled. In fact, even just empty space is entangled. So to understand how empty space is entangled, the first thing you have to understand, of course, is that in quantum mechanics, empty space has properties. It's not really so empty. It can have virtual particles in it. It has fluctuations of the field. In classical physics, the vacuum, the state with nothing in it, the state with no photons or no radiation in it, the electromagnetic field, for example, is just plain zero. It's just plain zero. There is no electromagnetic field. But in quantum mechanics, in the empty space, the field fluctuates. Sometimes you look at it, it could be positive. Sometimes you look at it, it could be negative. Translated into photons, some of the time in a little box someplace, you might find a photon if you look for it, even though we're talking about empty space. Sometimes you would not find a photon. All right, so if you take empty space and you make measurements on it, you get non-trivial results. Not just zero, but you sometimes find a particle, sometimes you don't find a particle. And here's what entanglement has to say about empty space. Let's divide empty space into two halves. I'm using the blackboard to represent empty space, the left side and the right side. And let's divide the space into little cells. And in particular, I'm interested in cells that are near the boundary. I'm not really doing anything. I'm doing a mathematical imaginary operation, both in dividing the space down the middle and in making believe that it's made up of little cells. But now we can do a measurement of the field, or we could look for a virtual particle. We could look for one of these vacuum fluctuating particles in here, and we could look in here. What we find is that if there is no particle on the right side, there will be no particle on the left side. If there is a particle on the right side, there will be a particle on the left side. So we could write the quantum state of these two here by saying if one of them is empty, call it zero, then the other one is empty. If we find a particle in it, then we will find another particle in the other hole. That looks very much, where did I erase it? That looks very much like an entangled state here. You can find out by looking in the left little cell here whether there's a particle here, just by the correlation between them. This is a form of entanglement. And it's a form of entanglement that's there in empty space between parts of space.
Are we assuming any scale between these two cells? Are they very close? Can they be
Yeah,
anywhere?
they begin very close. But we can also look at larger ones a little bit further away. And we find that they're entangled with each other. This with this, this with this, this with this, in pretty much the same pattern. And in fact, there's a general pattern. It's called scale invariance or conformal invariance. And we find that regions are entangled with each other if they're near each other. This one over here is not entangled with this. To make a measurement of a particle in here, you'll find out nothing about this. It's just too far away. But you will find out if there's a particle here, there's probably one here. Same thing in this bigger box here. If there's a particle in here, there's probably one in here. If there's one in here, there's probably one in here, and so forth. Okay. So this there's a pattern to this entanglement. And it's actually thought, this is a quantum property, but it really is beginning to be thought, I don't know how to describe this, except to say we think it's so fundamental that it, in a sense, holds space together. We know that if we were to destroy this entanglement can be destroyed. Entanglement can be destroyed by making measurements. There are all sorts of ways of destroying entanglement between systems simply by looking at the system. Once Art looks at his sugar packet and he knows which one it is, and he knows what he has, he now knows what Sanjay has, there's no more entanglement between them. They now know. There's no more, they know what they have. So by looking at the system, Art has changed it into an unentangled state. The same thing can be done in space. You can make an observation of all of these cells here and determine whether there is a particle in them or not, and that destroys the entanglement. It also does something else. It creates a huge amount of energy in the region where you made the experiment. Remember, in quantum mechanics, when you look at something, you change it, you affect it. And in this particular case, if you look at what's in here, you affect the system and you create a huge energy in here. Now, huge energies are sources of gravitational effects. They change the geometry. They change what space actually looks like. And in fact, they disconnect the space. They disconnect the space. They sort of unzip it. Space is zipped together by entanglement. This is one of the things we've learned by thinking about gravity and quantum mechanics at the same time, that entanglement is important, in a sense, for holding the parts of space together. Without it, space would not have its nice coherent structure, its contiguous structure of parts being adjacent to other parts. So entanglement is not only a feature of electrons, it's a feature of everything, including empty space. Now, entanglement has another property, one which is very important. It's called monogamy, the same kind of monogamy that I hope you people all enjoy, that I have enjoyed. What does entanglement of monogamy mean? No, monogamy of entanglement. It's easy to explain if you have 3 qubits. Imagine you have 3 qubits. We can call them Alice's qubit, Bob's qubit, and Charlie's qubit. Alice, Bob, and Charlie are quantum physicists' way of saying A, B, and C. Alice, Bob, and Charlie. So each one has a qubit. Actually, we could call A Art, couldn't we? Right, but then as we have to do S for Sanjay. All right, Alice, Bob, and right. Now, it could be that Alice's qubit and Bob's qubit are entangled. And that means that Alice can look at her qubit and find out information about Bob's. They're correlated. In fact, anything about Bob's qubit, Alice can find out by looking at the appropriate thing for her qubit. But they will find out nothing about Charlie's qubit if Alice and Bob are entangled. On the other hand, it is possible for Alice and Charlie to be entangled, in which case Bob is the third wheel of the, what do you call it when three people never, yeah, mélange de trois or whatever. A love triangle, right? A love triangle. So you can only be, technically I'm talking about something called maximal entanglement, but let's just call it entanglement. When two things are entangled, they are entangled with each other and they cannot be entangled with a third. That's the monogamy of entanglement. And it's a deep and basic principle of quantum mechanics that entanglement is monogamous. Okay. Now I've actually taught you enough to explain a paradox. The paradox is a very deep paradox. Among physicists, it's sometimes called the Amps paradox. Amps does not stand for a unit of electrical current. It stands for four physicists: Almeri, who was a graduate student, Marolf, and who's now here as a postdoc, Marolf, who's a famous general relativity expert, Polchinski, who's just a famous physicist, and Sully, who was also a graduate student who contributed to the study. They discovered what looked like a very fundamental paradox about black holes and entanglement. So I'll tell you what that paradox is. You start with a black hole. A black hole has a horizon. The black line represents the horizon of the black hole. Inside is the interior of the black hole. Outside is the exterior of the black hole. Interior is inside, exterior is outside. And according to Einstein, according to the general theory of relativity, the horizon is just a point of no return. Things can fall through the horizon. Things can fall through the horizon, and when they pass through the horizon, they just find an empty space. Empty space, vacuum. The horizon, or the vicinity of the horizon on both sides, just looks like a continuous space in which both sides are just the opposite side of a vacuum, of empty space. So this means somebody falling into the black hole will simply experience nothing special. Now, but we've already found that if things are like empty space, nevertheless there is this entanglement. Now, these things are not easy to measure. You don't go and measure a vacuum fluctuation with a, I don't know, what do you use to measure things when you want to measure? A ruler or a, whatever. What?
A multimeter.
A multimeter, right. Right. You got to be delicate. It's hard to do, but you can do it. So when, who do we send into the black hole? This gets to be a question now. Do we send Bob into the black hole or Alice? I usually send Bob into the black hole. I used to send Alice in, and then I got a lot of complaints about it. So we're going to send Bob into the black hole. Now, Bob is going to do experiments as he falls through. Maybe he's even going to make an experiment like one of these experiments here. And he ought to find that space, the properties of space, are very, very similar to what they would be in the empty vacuum not really being so empty. So, if that's true, then as he falls through, he might make a measurement of what's going on over here. He might look, for example, for a virtual particle, and then he might also make an experiment over here. And these two experiments, or these two degrees of freedom, should be entangled. Why? Because empty space is entangled in this way. So let's label the things that Bob could measure. Let's call this one B, and this one A. These do not stand for Bob and Alice now. They are just in front of the horizon and behind the horizon. Now I use B and A because we've been using B and A for these for a long time. B and A, they could stand for Bob and Alice, but we already agreed that Bob was the one who went into the black hole, so it's screwed up notation. Okay, Bob, but that's not Bob. That's just a little vacuum fluctuation over here, and the other one is a little vacuum fluctuation over here, and they ought to be entangled. Okay. But let's suppose that for one reason or another, and I'll give you a reason in a moment, that this black hole happens to be entangled, highly entangled, with some other system over here. How could that be? How could it have gotten entangled? Well, let me give you an example. The example that AMPS used was this black hole might have evaporated for a period, and if you collect together all the evaporation products, they will be entangled with the original black hole. But we don't need to do that. We could do it more simply. We could imagine, since we're in the business of Gedanken experiments, thought experiments, and the purpose of thought experiments is to analyze the consistency of principles, we can build these black holes to be entangled from the first place. I showed you a little while ago how you can create two macroscopic objects which are entangled. You simply create them out of material which was entangled to begin with. Particles which individually, this one with this one, this one with this one, were entangled. So you do the same thing. You collect these entangled particles in buckets. Each particle in the left is entangled with something in the right. And then you create enough of them that gravity pulls them together and makes a black hole out of each side. That's something we think should be, in principle, possible. If we do that, what we wind up is with two entangled black holes. We have two entangled black holes, which means everything about this black hole, whatever it is, anything you might want to know about this black hole, you can measure by making a measurement in this black hole. These two could be arbitrarily far apart. These entangled pairs could have been separated from here to the moon, or from here to, that's not very far, from here to Alpha Centauri, or from here to 10 billion light years away. They're still entangled, and you can find out anything you want about one of them by looking at the other carefully enough. Okay, so let's do that. Let's assume that somehow these two black holes, we're going to be black holes now. This is what Alice has control over, and Bob is over here someplace. Now we have a problem. We have a problem because I told you in the beginning that this black hole, everything about it, every little bit of it, is entangled with something in here. But I also told you that for the horizon to make sense and to look like empty space, the things just on this side of the horizon have to be entangled with the things on the other side. And now we have a monogamy problem. The monogamy problem is that B is a bigamist. And bigamy is forbidden, not only by law, but by physical law. So something's wrong. Something's wrong. One possible answer is that if a black hole is created entangled with another object, it doesn't have to be another black hole, it could be anything. But if it's, in particular, if it's created entangled with another object, then something happens to the interior of this black hole and wipes it out, creates nothingness in here. By nothingness, I don't mean empty space. I mean nothing. And that means that if somebody fell into it, they couldn't fall in because there's nothing there. That's called a firewall. The idea, a firewall of the kind that creates an absolute barrier to where anything could go from outside the black hole to inside. No inside, because if there was an inside, and in particular, if it was possible to pass smoothly through here as if the horizon was empty space, this would have to be entangled with this. But by assumption, it's entangled with that. So we have this problem. And the conclusion that AMPS drew Almary, Polchinski, Marolf, and Sully, was that what this means is that if a black hole does, for some reason, become entangled with another system like this, it just doesn't have an inside. There is no inside. On the other hand, everything we knew about general relativity, everything that Einstein taught us, said no. The interior of black holes exist, makes just as much sense as regions of space as the outside, and somebody falling in should fall in smoothly. So this is a paradox. And it's a real paradox. It's a genuine one. The solution, I don't think, and I don't think too many people, including the inventors of the paradox, are at all convinced that their solution is right, the firewall solution, but it's a real paradox. And it's a thing that has driven me for the last 2 years. This is conflicts of principle. This is conflict of principle between Einstein general relativity on the one hand and quantum mechanics on the other hand. Conflicts of principle like this, when they're unraveled and when one understands what's going on, often lead to the biggest advances in our understanding of physics. So this can't stay that way. You can't just leave it and say, oh, well, okay, it seems like a paradox. It's really at the core of things, at the core of the relation between gravity and quantum mechanics. Okay, so let's see, what is the possible solution? We'll talk about possible solutions.
Could you say again quickly how B became a bigamist?
How B became,
A bigamist.
well, we're postulating somehow that B, remember, when a thing is highly entangled like this, and this was created in this very entangled state, you can find out anything about what's going on in this black hole by looking at what's going on in this one by construction. We constructed it that way. So we constructed the black hole in such a way that B is entangled with something in Alice's system here. That means there's something or other that Alice can measure in her system that would tell her about B. On the other hand, if the horizon really is smooth, if the horizon really is like empty space, if it really is like empty space, then the properties of quantum field theory, the properties of just the quantum mechanics of empty space says that B has to be entangled with A.
So B is one of the black holes that don't.
B is not a black hole. B is just is one of these little cells. It's just one of these little cells that somebody could make a measurement. Just a little piece of empty space. A little piece of empty space. As Bob falls through the horizon, here's the horizon right over here, it makes a measurement of whether there's a particle here and then whether there's a particle here. A vacuum particle, a vacuum fluctuation. And those things, in order for the vacuum not to be messed up badly, would have to be correlated and entangled. That's what we learned by understanding quantum field theory. Okay, so if the horizon is what we always thought a horizon was, just a point of no return, but not in itself some sort of terrible environment, then this little region of space over here has to be entangled with this little region of space over here. On the other hand, by construction, everything about this black hole was entangled with something in Alice's system over here, which could be another black hole. Let's take it to be another black hole. B can't be entangled with both because of the monogamy property.
Why isn't it A that's entangled with the external system? A is the one that's going into the
A is behind the horizon, and in our current understanding about thinking of black holes, the basic quantum state is composed out of things outside the horizon, and the interior is built in some other way. But you might just say that everything about this black hole, including B, has to be entangled with something here, and therefore, how can it be entangled with A? Now, there's one way. These are bits of information. They're logical bits, if you like. They're logical possibilities. You can say, does A have a particle in it, or doesn't A have a particle in it? But you can just say it's like an abstract bit of information. Could it possibly be? What's that?
Why does it have to be a black hole? I mean, even in normal gravity,
Which one have to be a...
the left side one.
The left side one, if this weren't a black hole, we wouldn't be talking about its interior. We wouldn't be talking about its horizon.
But any 2 points generally would be correlated. And correlation still exists. What makes the black hole special? I mean, what makes A different from normal 2 points in select? I mean,
The belief... Sorry, what makes the black hole different than what?
No, in the sense like if I consider 2 points in the normal gravitation
Yeah.
of Earth, then these 2 points should be correlated. And
Yeah.
if Earth is created out of some...
Yeah. So you say, oh, I see what you're saying. You're saying, for example, supposing this was just empty space, and this has to be correlated with that. Is that what you're asking? But supposing we knew that this empty space was also entangled with something over there. The answer indeed would be, if we knew that this was entangled with something over here, then we would know that it wasn't entangled with this, and we would expect a mess in here, a terrible mess in here, which would not look like empty space. We would have to do, it's very, very difficult to unentangle these two things here. But it's a puzzle for black holes because black holes have horizons, and horizons are supposed to be smooth. From all we ever learned about black holes, they're supposed to have these smooth horizons. If we took just a chunk of matter and we did this, we'd probably make a big mess out of it over here, which is exactly what we don't want to do for the black hole. So the question is one possible answer is what the AMP said, that a black hole, which is entangled with another thing, develops properties which are very different than what Einstein said black holes are like. Now remember, one way of entangling the black hole with something else is just to let it evaporate for a while. Black holes evaporate, Hawking radiation. As they evaporate, incidentally, this is something that any system will do. It will eventually evaporate. It could be a puddle of water. A puddle of water, H2O, will also evaporate. Let's suppose it's completely isolated in outer space, a little puddle of water, and little droplets will go off. The little droplets will be entangled with the puddle. As the puddle shrinks, it will become entangled with the outgoing products of evaporation. Eventually, when there's enough evaporation product out there, the bubble here will be highly entangled with what's out here. Right? So the way that AMPs imagined it, they imagined this object over here was really just the Hawking radiation that went out. Now you could take that Hawking radiation and collapse it into a black hole, it would still be entangled with it.
How does monogamy work with the H2O example? I mean, you're saying it's entangled with all the evaporation products?
Yeah, it would just actually be entangled with the outgoing radiation, and different parts in here would not be entangled the way you might have expected. And it would just be true. But there's no such thing as a horizon, and there's no reason to think that there ought to be a smooth horizon. So it only comes up as a crisis when you think about black holes. Again, it could simply mean that the black hole doesn't have an interior. Nobody wanted to believe that. I think very few people do believe that the black hole doesn't have an interior, and it certainly violates the principle of equivalence of Einstein. And so the question is there no other way out? Is there no way that this somehow could be misleading? Well, there's one way out. As I said, these are logical qubits. These are logical bits of information. And a logical bit of information over here, which is the thing we called A, which is supposed to be entangled with a logical bit of information over here, despite the fact that the logical bit of information over here is entangled with something else. Let's give it another name, B prime. B and B prime are entangled. We built the thing that way. B is supposed to be entangled with A, but there's something wrong. There is one way out, and that's that A and B prime are the same thing. A and B prime really are the same thing. Is that possible? Is that completely nuts? Amps said that's too crazy. They're too far away. This object could be off an Alpha Centauri, this black hole, let's say on Earth, and the thing which is right behind the horizon over here is clearly near Earth. It's not near Alpha Centauri. So it doesn't really make sense to say that A is really the same object that's out here. But they also had an experiment that they imagined. Here's the idea. The idea is that a bit of information just behind the horizon here is really the same bit of information as over here. Okay, so here when various people said this and said maybe this is what's going on, the answer of Amps was very, very clear. They said, no, that's complete nonsense. And here's the way to prove that it's nonsense. Supposing A really was the same as B prime, and B prime is off on Alpha Centauri. Well, Alice, who was at this end, could make a disturbance of B prime. She could measure something in B prime. Measuring things disturbs them. So by Alice manipulating the B prime, which is in this black hole someplace, the thing which is entangled with B, by measuring it, right? First of all, she has found out something about B, but by assumption, she has effectively measured something just behind the horizon of the black hole. Well, that's crazy, because by making a measurement of something, you disturb it, and the result would be a disturbance just behind the horizon of the black hole. Amps said, and a disturbance means some energy deposited there. Some energy deposited there by the measurement. Anytime you measure something, you tend to change its energy. So by measuring what was out here, you made a disturbance over here. Well, how crazy. One of them is off on Alpha Centauri, the other is over here. That can't be right. Or you can say one of two things. By measuring what's out here, perhaps you did create a particle behind here. But that's, as I said, that's a little bit crazy. It's too far away. So if there was a particle behind there as a consequence of Alice doing something over here, that particle must have been there whether or not Alice made her disturbance. She's just too far away for it to matter. And so the conclusion was that there must be loads of particles behind here, one for each possible measurement that Alice could possibly do on this thing. That's what was called a firewall, and that was the basic paradox. That was the unhappy paradox that Amps concocted. There was one assumption here, and it seems so obvious that, that it was obvious. Namely, that there's no causal connection between this black hole or the environment of this black hole. I draw a little bubble over here to indicate the thing connected with this black hole. That there's no causal connection between the bits of this black hole and the things which are behind the horizon over here. In other words, there's no causal connection means a way of disturbing things over here that will show up over here. And that seemed obvious to everybody, except it seems that it's wrong. It seems that it's wrong, and to understand why it's wrong, we need to think about on the other half of the EPR, ER connection. This was all about entanglement in the context of black holes and a puzzle about entanglement. The other paper from 1935 had nothing to do with quantum mechanics and had to do with the geometry of the interiors of black holes. ER invented something called an Einstein-Rosen bridge. I don't think they called it an Einstein-Rosen bridge. It was called Einstein-Rosen bridge afterwards. And what they did was they looked at the mathematical solution of Einstein's equations that I don't know how they managed to look at the Kruskal solution before Kruskal was born. I'm not sure, but somehow they did. And they knew enough about general relativity. Einstein was pretty good at general relativity. But for those who know what a Kruskal black hole is, it's basically a black hole. I'm going to draw the Penrose diagram of it. Now here we're coming to things that I'm going to assume you know a little bit about, but I'll explain them a little bit as we go along. That's a space-time picture, time going up as usual, space going horizontal. It's a space-time map of a black hole. Let me explain it to you. On these kind of diagrams, light moves at 45 degrees. Light moves at 45 degrees, either outward or inward. If you're out here, this is spatial infinity. This is spatial infinity. When I say it's a map of space and time, it's a distorted map of space and time. It's distorted in the same way that a Mercator projection of the Earth is distorted. It's squeezed around in such a way as to be able to put all of space-time on the black hole. So this is very far away over here, off at infinity. This is time infinity. The clocks go to infinity up here. Here's the horizon of a black hole, and here's the exterior of the black hole. The only thing you should notice is if some poor person happens to fall through this line here, they are trapped. This is the singularity of the black hole, and it's a bad place. It's a place where you won't survive. This is the horizon of the black hole. If you fall through there from the exterior region, you're dead. You're doomed, anyway. You may not be dead, but you're doomed. You're going to hit that singularity there. Now, this is the exterior of the black hole, but strangely, the black hole seems to have two exteriors. One on this side and one on this side, and you can fall through from this side or that side. Well, it's really two black holes. It's a black hole on this side, and it's a black hole on this side. They're, in a certain sense, infinitely far away from each other. You can't go around from one side to the other. You'll never get there. Here's a picture of what this Kruskal extension, and in what sense it's two black holes. It really represents two disconnected regions of space, completely disconnected. Here's a region of space, or a space. That stands for space. Not space-time, but space. X. That's the right side. The left side, another region of space. And connecting them, you can go from one to the other by passing through something that John Wheeler called a wormhole. When you walk from here to here, right through that point, you walk through the horizon of one, and you show up just outside the horizon of the other. That's over here. There's the horizon. So falling in, or crossing over, not falling in, but crossing over from here to here is crossing from here to here. Einstein and Rosen drew this picture. Somebody called it an Einstein-Rosen bridge, and it stood for this diagram over here. It's two completely disconnected worlds that are only connected by virtue of this wormhole. Okay? It's a real solution of Einstein's equations. It exists. It exists mathematically. It has some properties. First of all, the region over here, as you cross from here to here, is pure empty space. Nothing strange going on there. If you were able to pass from here to here, you would find nothing strange there. It's just empty space. That implies that there is entanglement between this side and this side. Entanglement across here. Another way to... Yeah, if you actually wanted to walk across there, yes, you would. But But we're not really walking across there. We're just talking about the properties of space from one side to the next. I don't really imagine walking across there. I imagine a series of observers over there making measurements, and then they could correlate their measurements by sending signals into the interior here. So they could ask somebody on this side and somebody on this side making measurements whether this side and this side are entangled. They're supposed to be entangled if space is really just flat over here, if space is just empty over here. And that says that in this picture of what's going on at an instant, there must be entanglement between one branch and the other branch. In other words, to put it another way, this represents two entangled black holes, one over here and one over here. Now, they're on two completely disconnected spaces. You can't go around the outside, forget going through the interior. Can you ever go from here around to here? No, because they're just disconnected. They're not a connected space. But you can do the same thing in another way, or a very closely related thing. Imagine a very big space. But I'm going to draw it in a funny way. Here's space. Okay? It's big. I'm just going to fold it like this. Now, that's not really done anything to it. It hasn't changed the geometry, the geometric relations. It's just a way of exhibiting it. If I had space very big and I might want to pull it all into this room, a big sheet of cardboard, big, huge sheet of cardboard, I might want to bend it over like that to get it into the room. It doesn't change any of the relationships on the cardboard. So we do that. We take a big region of space and we bend it over. Let's see if I can do this right. You can see the picture. I haven't really done anything to it. I've just exhibited it in a way that gets it all in a small region here. And then we take one of these Einstein-Rosen bridges and put it between here and here. These are, as far as the external world goes, these are two black holes very far from each other. You might have to go a zillion light years to go from here to here around the outside. But strangely, it has the property that you cannot go through the Einstein-Rosen. This is one property of Einstein-Rosen bridges that is important. You can't actually pass through them. You can see that. Where's our diagram? Here's our diagram. Can you get from this side to this side? Can you get from here to here at all? No point on this side over here can send a light signal that will ever get to this side. No point can send a signal that will get to the other side. But what can happen is they can meet at the center. So the meaning of that is, although you cannot send a signal through the Einstein-Rosen bridge, somebody could jump in from the side and jump in from the side and meet at the center. Same thing here. If somehow this kind of thing could be manufactured, then these two places could be, as far as the external world goes, it could be 10 billion light years or more around there. Light years. And yet, if Alice jumps into her black hole and Bob jumps into his black hole, they have a chance of meeting at the center. That's a very crazy thing, but it's a consequence of Einstein's equations. What do you need to do to make two black holes that have this kind of connectivity? The answer is they've got to be entangled. If they're entangled, then they will have exactly this kind of connectivity. So if you can make black holes which are entangled, and you can make them by taking entangled collections of particles and collapsing them into black holes. They have the astonishing property that in principle, no matter how far apart you take them, you can do things to them and then jump into them and meet at the center, and not in a terribly long time, but almost immediately. This was always considered a kind of science fiction-y thing. But it is an actual property of Einstein's equations together with the ideas of entanglement. If you could make two entangled black holes, they will have this property. Okay, so now we can come back to this crazy entanglement story. Let me draw it one more way. Let me draw one more way of thinking about these entangled black holes, which are very far from each other. Let's not fold over space in that way. Let's just take flat space, here it is, big, and put a black hole over here. Here's the inside of the black hole, here's the horizon, here's the inside of the second black hole, there's the horizon. What we're talking about is a geometry. What the Einstein-Rosen bridge is it's a geometry that if you fall into here, you come out over here. Let's redraw it. Well, you can see. If you fall into one, you appear in the interior of the other black hole. This point and this point are not really far apart. They're both inside, but Alice and Bob can jump in and discover. Right. The one thing you can't do is use this to send information from outside this black hole to outside this black hole. That will not work. But you can use it to send information from outside this black hole to the inside of this black hole. The only way Bob on this side would ever know about it is if he was willing to jump into the black hole. This kind of connectivity, first of all, is the real properties of solutions of Einstein's equations. It appears that it is closely connected with whether the black holes are entangled, and it basically resolves this puzzle. It basically resolves this puzzle by mucking around with things over here and doing disturbances. In fact, what will Alice do? If she makes a disturbance over here trying to measure something, odds are she will disturb something and send something into her black hole over here. If the two black holes are entangled, the disturbance will appear right on the other side here.
So, does the solution to the paradox you mentioned?
That's the solution. That is. When I say it's the solution to the paradox, I do not mean to say that everybody accepts it. It means to say that this is a.
One of the things you mentioned was
Yeah.
if P and B prime go to the same point,
Yeah.
then the paradox gets resolved, and I'm just tying that to.
Not if B and B prime are the same. If B prime is the same as A. Well, if they're close and can influence each other easily.
No, so carrying it on to the space-time world, does it mean that therefore, if you jump in on A, you come out of B prime?
If you jump into A, you will not come out of B. You see that? We come back to here. If you jump in from this side, you will not get to the outside of the other one. All you'll do is get into this side, into the black hole on this side. On the other hand, if Alice also jumps in, or Bob, I don't remember which one is Alice and Bob, they can meet at the center. Okay? Not unless you're willing to jump in. Right.
But wouldn't that be the main point, is you can never know if this is true? Because assuming we're outside the black
Yeah.
hole by definition,
Yeah.
so it's an irrelevant experiment, or a thought experiment in some ways. We can never know. The information can't be verified, you can never resolve the entanglement. So the information can't flow out.
Unless you're willing to jump in.
But then you're inside, and then...
Yeah. Nobody's going to do this experiment. We're trying to unravel an inconsistency. We're trying to unravel an inconsistency between two principles. And what we're finding is there's no inconsistency. But what you have to accept is that there can be this kind of connectivity, spatial connectivity, surprising, unexpected spatial connectivity as a consequence of quantum entanglement.
Is a non-zero amount of space-time required for entanglement to be present?
I think what this is saying is that in a certain sense, entanglement builds space-time. Anytime you have entanglement, a bit of this kind of thing happens and builds a kind of space-time between the two things. Now, if they're just electrons and they're entangled, nobody's going to jump into an electron. You can't get Alice and Bob to jump into different electrons at different places. The only content of the entanglement is the usual content of entanglement. What this is saying is somehow when entanglement gets big enough between big enough macroscopic objects, when it becomes big and entanglement between big macroscopic objects and those macroscopic objects are made very, very dense, that entanglement turns into space-time, turns into new regions of space-time that were not there if the systems were not entangled. Now I think this is not too contentious. I think most of theoretical physicists who are working on these things more or less believe this.
But naively, you're saying essentially that entanglement is more fundamental. So entanglement creates space-time. But
I don't know that I
there
want to say which
there
one
can
is-
exist things in space-time that are not entangled.
There can exist things in space-time which are not entangled, and there will be no spatial connectivity of that type. You can have two black holes which are not entangled. Absolutely, you can have things which are not entangled. Two black holes which are not entangled will not have this peculiar feature of a connectivity between them like this. Bob will jump into this one, Alice will jump into this one, and there is no chance at all that they will meet at the center if they're unentangled.
On that Penrose diagram, isn't that assumed that the black hole existed from the beginning of time minus infinity?
Good point. Yeah. This diagram, yes. But you can imagine that the upper half of this diagram, let's take the upper half of this diagram, well, in this fashion over here. That the upper half of this diagram represents the following process. You started over here in a sort of neutral position, neither on the left or the right, and you started creating entangled pairs. Lots of entangled pairs. Electrons and positrons, if you like, any way of making entangled pairs of particles, and that's easy. And then you take half of each pair and bring them over to here, and half of them over here. And remember that these are entangled with these. Let's represent the fact that they're entangled by drawing lines between them. This is simply a notational device to say this particle is entangled with that one, this one is entangled with that one, and so forth and so on. No content to this other than whatever content is supposed to be associated with this entanglement. Then having done that, we now collapse them into a black hole. We make enough of them so that either their own gravitational field will cause them to gravitate and form a black hole, or we compress them. We put them between the jaws of a vice and we squeeze them down until they form a black hole. And lo and behold, these vertical lines here effectively coalesce into something when there's enough of them that they form a new region of space. It's the emergence of a new region of space out of quantum entanglement. That's what these things are saying. That we're learning that enough entanglement in a small enough volume will manifest itself as a new region of space that now has the possibility not of communicating from the outside to the outside, Entanglement never allows that, but communicating between the outside of one and the inside of the other. Yeah.
If you had two pre-existing black holes and you sent one entangled bit to one and one entangled to the other, does that make an Einstein-Rosen bridge?
Yes, so we have an Einstein-Rosen bridge of about 1 Planck area. Yes, that's a good question. You have two, that's a very good question. You start with two black holes which are unentangled, and you take a, entanglement is not a thing which is either yes or no. There's a magnitude of entanglement. The magnitude is called the entanglement entropy, but it's basically a measure of how many entangled pairs are shared between the two sides. All right? If you took one entangled pair and dropped it into here and into here, then yes, you would make a very, very primitive Einstein-Rosen bridge for which there is no particular meaning other than the fact that they're entangled, but you could draw it by saying there's a very simple, primitive, Planck scale, tiny, tiny microscopic bridge between them. And, but I assure you, nobody is going to jump into there and meet at the center. So you can ask, how many do you have? Well, you can ask, how many do you actually have to assemble before you can make something big enough that people could meet at the center? And the answer is this, that the number of entangled pairs manifests itself in the area, in the minimal area of the bridge. So if you want to make a thing with an area that's big enough for you to fit into, you have to have started with enough entangled pairs that, that you'll make a big enough area. Something like, let's see, I think 10 to the 76th of them, 10 to the 72 of them, in order for you to fit in through the bridge. So that's right. Right, exactly. So it's not easily done.
Does every element in the universe have an entangled partner somewhere?
Not particularly. But probably in practice, yes.
Does our manufacture of an entangled pair do something to space-time? Or going the other way around?
It only has an appreciable effect on large-scale space-time if the entanglement is strong enough. Only when you collect enough entanglement like this and collapse it do you make anything resembling ordinary space-time. But yes, I would say yes, that is right.
Does the fact that the time goes to zero at the horizon play any role here?
The idea that time goes to zero at the horizon is just a statement that that's a point over there. It does play a role, but the main role that it plays is saying that you can't escape outside. You can't escape from the inside to the outside. Or better yet, you can't pass from the exterior of one to the exterior of the other. All right, so the lesson to learn here is that the connectivity of space can be more interesting and more involved, more topologically interesting as a consequence of entanglement, and that does resolve the Amps paradox. Whether Amps themselves would agree, I know the answer to that. They agree when I'm around. That's all I know for sure.
Where is the singularity on the orbital space?
Oh, no, this is kind of a slice through the center here. Now you can ask what happens. All right, good. There's an interesting issue here of what happens as time evolves. This is the slice right through the middle here which you can sort of think of as what happens when you first collapse the particles into the black hole. When you first take them, first they're particles, and then you collapse them, and you make this thing that's just straight through here. So let's look at it. Starting here, I'm not literally walking, I'm just moving my finger from one side to the other. And going from here to here, what you're doing is going out from out here through here, that's this point over here, and then going through and coming back out. But you can't do that without exceeding the speed of light. Okay? Nevertheless, there's an imaginary excursion walking across there, that's this. So this picture is what happens at t equals 0 when the horizons are just touching. Okay. What happens later? What happens as time goes on? And we're going to talk about this next time in greater detail, but as time goes on, the interesting part of the Einstein-Rosen bridge is the part behind the horizon. Once you fall through here, you're stuck in the interior of the black hole. You can't get out. You're going to hit the singularity. So this is the extended horizon over here. This is the extended horizon on the other side. And the interior of the Einstein-Rosen bridge, or the interior of this object, is what's in here. Now, notice an interesting property. As time goes forward, let's just draw time going forward like that, the Einstein-Rosen bridge grows. It started with the horizons touching each other. It started, let's draw it this way. Right over here, the horizons are touching. That's what happens as you move in, you get to this point over here, that's right over here, and then you go out the other end. Okay. At that point, at time t equals 0, the Einstein-Rosen bridge is as short as it can be. As time goes forward, the horizons start to separate. The two horizons of the two black holes start to separate and leave between them a region of space. So what does that look like? That looks like this thing starts to grow. It starts to stretch. It doesn't shrink, but it starts to stretch. If you work out Einstein's equations, you will discover that the solution grows and grows and grows. And in fact, in going from up here to across here, it's infinitely far, way up in these corners here, way up in these corners. So as time goes forward, this Einstein-Rosen bridge grows. Its growth is one of the reasons that you have such a hard time sending a signal completely through the Einstein-Rosen bridge. You can't, and it's because as you're trying to send a signal through, it's growing. And it's growing fast. It grows basically with the speed of light. So the Einstein-Rosen bridge grows with time. It's a very interesting question. What properties of the quantum mechanics are encoding this growth of the Einstein-Rosen bridge? This is the problem. All right. The resolution of the original Amps paradox is essentially that there is a causal route. It's through the wormhole, if you like, a causal route from the edge of this black hole over here to the interior of this black hole. It's sort of into this one and out over here. There's no problem left once you buy into that. Okay? But there's still something interesting to understand. What is it about entanglement? What is it about quantum mechanics? What is it about the nature of these systems that encodes the fact that the Einstein-Rosen bridge grows with time? It grows, it doesn't shrink. And how long does it grow? Classically, according to classical general relativity, it grows and it grows and it grows forever, getting longer and longer, with its length being proportional to the time. That's a puzzle. That's another puzzle. It's a new puzzle. And the reason it's a new puzzle goes something like this. Black holes are thermal objects. They're objects with a temperature, with an entropy, and they're in thermal equilibrium. Well, they don't start in thermal equilibrium. When they're created, they're out of thermal equilibrium. But thought of as quantum mechanical systems, they're systems which are thrown together and very quickly come to thermal equilibrium. The time that it would take a solar mass black hole to come to thermal equilibrium is basically about a millisecond. A big solar mass black hole, a couple of kilometers big. When it collapses, it's way out of equilibrium. Why? Because the sudden collapse is a sudden process. Way out of equilibrium, thermal equilibrium. And then the internal dynamics of whatever it is that's making up the black hole equilibrates, and it takes about a millisecond for a solar mass black hole to come to thermal equilibrium. Very, very fast. And then what happens to it? Let's assume nobody is poking around at it, but you're watching it from the outside, and you're describing it by quantum mechanics, you're describing it by a combination of quantum mechanics and whatever else describes it. What do you find happens after that millisecond to the black hole? The answer is nothing. Once things come to thermal equilibrium, nothing happens. That's it. That's about all that ever happens. Once you come to thermal equilibrium, the evolution of systems just ceases. Unless you disturb them again. Unless you disturb them. Unless you do some disturbance to them. It's also possible for accidental fluctuations to take place. Let's talk about thermal equilibrium. My favorite example is the air in the room. Let's take all the people out of the room so that we don't disturb the system, and start with some very strange configuration of the air. The usual configuration people like to talk about is all the air in the corner of the room. That's way out of equilibrium. That's like the black hole just being allowed to collapse suddenly. And then what happens? The air eventually fills up the room uniformly, and then nothing happens after that. All sorts of interesting things happen in between, but nothing interesting happens after that. The air just fills the room. So thermal equilibrium is usually thought of as the end of interesting things happening. And it happens fast. It happens fast. In this room, it would probably take a couple of days for the air to really equilibrate. But in a black hole, because of the compactness of it, and how strongly the different pieces of it interact with each other, it happens very fast. So after a very short amount of time, somebody looking at this black hole will discover that it simply stopped, or if it was created by a process like this, a process of collapse, they'll discover nothing happens afterwards to the black hole, looking at it from the outside. If that's the case, that nothing interesting happens after thermal equilibrium, then how do we account for the fact that the interior of the black hole grows and grows and grows forever? What's going on that simultaneously allows us to say that from the outside of the black hole, it thermally equilibrates and nothing flat, and yet that same quantum mechanical system, something is going on that says that it is evolving and evolving and evolving, the interior geometry evolving essentially forever and growing. How do we understand that? That's another form, that's another paradox that I think we'll take up next time. And it's the paradox of complexity, of quantum complexity. Now, as I said, I'm telling you what I think. The purpose of these lectures is for us to lay out what we're thinking about here. What you will find, of course, is that ongoing research, as it happens, generally does not involve consensus between everybody. So this is not a thing which has reached the stage of consensus, but this is what I think. This is going to go into a historical record. This historical record will be a record of the research that's performed at SITP by the various people who do it. And 100 years from now, historians will come and they will look at it. And what will they say about this? We'll find out. Hopefully, this record will be of some interest to people. It'll be public. It'll be available. And I'm hoping it will be interesting. Anyway, let's see. Should we go on a little bit or not? Yeah, let me tell you a little bit more. How do you make entangled black holes? Well, I told you one way to make entangled black holes is to take a bunch of entangled particles and then collapse them. But it's by no means obvious that that makes a black hole with a wormhole, two black holes with wormholes between them. That's a sort of guess. But there is a mathematical or physics-oriented process that when you actually solve the equations, you do discover that you've made two black holes with a wormhole between them. And this is an old process. I'll tell you about it. By a process, I don't mean, could you do this in the laboratory? In principle, yes. In principle, yes, this could be done in a laboratory. It would be very hard and would take a long, long time and involves very, very difficult conditions. But I'll tell you what the process is. You start with a very primitive and simple version of it. It was discovered by Julian Schwinger. Julian Schwinger was one of the great discoverers of quantum electrodynamics. And it's called pair creation in an electric field. Pairs mean electron-positron in an electric field. You take an electric field, a big one, capacitor plates, plus, 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 minus, 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 minus. You put enough charge on them to make a very, very big electric field. Now, one of the problems with this is that you couldn't make such a big electric field in the laboratory. It would simply discharge itself. You know, you'd blow up your laboratory if you tried. So, but in principle, you make a very, very big, and you can also do it with a magnetic field. But you make an electric field of very, very sizable big value. And what will happen is the vacuum fluctuations, the creation, remember, there are constantly in the vacuum the creation of pairs of particles. In particular, electrons and positrons, virtual particles, a minus charge and a plus charge. Then they form and then they collapse, and they form and they collapse, and they're constantly an ongoing thing. So supposing over here, right in the middle, a minus charge, an electron and a positron were created. Left without the electric field, they would just recombine. And these processes take place continuously in empty space. But the electric field exerts a force on the plus charge this way, and the electric field exerts a force on the minus charge this way, and it simply pulls them apart. Out goes a plus charge, out goes a minus charge. Now, of course, if you really have a capacitor, then the plus charge will get absorbed into the capacitor. But imagine this is so big that, these particles will fly a long way before we have to worry about the walls of the system. So we've created a pair of particles, pair of plus and minus. In fact, we've created an entangled pair. This pair is entangled in several different ways, but in particular, the spins of the particles are entangled. So we've created a primitive entangled pair. Now, if you really make the electric field big enough, you can do something which can be calculated. It is possible to calculate from the basic rules of quantum mechanics and field theory. You can calculate the pair creation of something much more exotic than an electron and a positron. You can calculate, literally calculate the process, means you can calculate the probability for it, and you can calculate how it behaves afterwards, of two black holes. A plus black hole, nope, a minus black hole, and a plus black hole. These are charged black holes. Black holes can be electrically charged. A plus charge black hole and a minus charge black hole. This is just an extreme version of the same Schwinger process. Right? Black holes, incidentally, have many quantum states. They're not like an electron, which has two quantum states, spin up and spin down. They have many, many quantum states. Many quantum states because they have a large entropy. Black holes have entropy, and so black holes have a lot of quantum states, just little rearrangements of them. The black holes come out, and like the electrons, they come out maximally entangled. They come out in such a way that you could learn anything about this black hole. Remember, black holes are not just objects. They're objects with many, many states, many things going on in them, complicated systems. They come out maximally entangled in the same way as the electrons, in such a way that in principle you can learn about anything in Bob's black hole from Alice's black hole. That's number one. So they're entangled. Number two, when you calculate the geometry, the solution of Einstein's equations that correspond to this, what you find is the solution has a wormhole between them. Exactly this behavior. Let's see, we can draw it on one of these folded pictures. Here's the folded picture. On the folded picture, on the folded strip, there's an electric field. The electric field could be pointing that way, a big electric field. And what happens is a pair is created. A pair of black holes are created, and the black holes are created with an Einstein-Rosen bridge between them. And then one of them is accelerated one way, and the other is accelerated. These are opposite directions, incidentally. This one this way and this one this way correspond to opposite acceleration, and this whole thing just slides off and eventually becomes two black holes very far from each other, which are entangled, and the Einstein-Rosen bridge moves with them. So that is a classic example. It's not classical, it's quantum mechanical, but it's a classic example of the pair creation of entangled black holes. You can then do this over and over again and collect yourself a large number of such pairs. So after a while, you have a whole bunch of ones going this way and a whole bunch of ones going this way. What would it look like? It would look like just a whole bunch of black holes connected by wormholes, connected by Einstein-Rosen bridges. The Einstein-Rosen bridges are hidden from our view because they're behind horizons. But then if you like, you can take them and you can collapse them into bigger black holes. And from following the structure of the Einstein equations, you discover that the bigger black holes are, number one, entangled, and number two, have Einstein-Rosen bridges between them. So this idea of entanglement being, if not identical to, at least a close relative of Einstein-Rosen bridges, this idea appears to have mathematical substance from a number of examples. We know other examples. And, we'll see. We'll see in 100 years whether it still stands. As I said, the next thing to try to understand, which is even stranger, in some ways even stranger, is what property of the quantum mechanical evolution of a pair of black holes corresponds to this growth of the Einstein-Rosen bridge. And We will talk about that next time. That's the subject of quantum complexity. Yeah.
So just two positron electron pairs that's entangled, they have a bridge between the two. Just two particles that are entangled.
Yeah.
They have an Einstein-Rosen bridge between them.
A very primitive one, which in some sense is no bigger than a Planck scale.
So is this at all related to the idea that a particle is actually a black hole? An extremal black hole, right?
Yeah. Yeah, but of course, a extremal black hole, it's an extremal black hole of 1 bit of entropy, the smallest possible. And even it's not really that either, but it's lighter than an extremal black hole. But yeah, it's related to the idea that there's no sharp separation between particles and black holes. Very definitely connected to that. Yeah. Yeah. You know, if you look at the spectrum of elementary particles, yeah, light ones, heavier ones, heavier ones, heavier ones, and eventually you get up to an energy which is a mass which is large enough for them to have an appreciable gravitational field. At that point, they basically are black holes. So the sharp division into what we call black holes and what we call particles is not really a sharp division. It's a qualitative distinction. As I said, you can't jump into an electron. You can jump into a black hole, but there's a gradation of different sized black holes, particles being the smallest and big ones being big. So that's a good point, that there's no sharp division between particles and black holes, and therefore there should be no sharp division between what we just call entanglement and what we call geometrical connectivity. Yeah.
When did that concept first arise? So you have a geometrical solution that creates a wormhole or an Einstein-Rosen bridge that implies two entangled systems that are far apart. Is that part of this AMPS paradox, or does that come long before the AMPS?
Well, I think it was really articulated clearly, most clearly after the AMPS paradox. But it was based on things that had been understood earlier, much earlier. There was a wonderful paper by a relativist by the name of Werner Israel in the early 70s who pointed out that this Schwarzschild-Kruskal version of a black hole here, the quantum state of it was a highly entangled state. Now, he didn't know what to do with it. He didn't have anything great to do with it, and it was more or less forgotten until Juan Meldacena, who is, largely the hero of all of this to my mind, brought it up again in the context of modern string theory and modern ideas, and realized that these two disconnected black holes on two different sheets that the connectivity between them, the fact that you could send a signal through here, even though they were in some sense in completely non-interacting worlds, was a consequence of the entanglement. But in the context that we're talking about here, it dates to much more recent than that. It dates to a paper of Meldacena and myself. But it was, there was an evolutionary growth of these ideas. These ideas don't suddenly spontaneously appear from nowhere. The idea that it was a solution to the AMPS paradox, that was a paper by Meldacena and myself about a year and a half ago. But the growth of the idea of the connection, so let's see. There were a very important observation by a young physicist, not so young anymore. He used to be a young physicist. In fact, he used to be a postdoc here, Mark van Ramsdonk in Canada, who I think you could probably say it was his basic idea that entanglement is what holds space together. And that when space is held together, it's always entangled. And when it's entangled in the right kind of way, it means that things are juxtaposed in a smooth way. So Van Ramsdonk, and this is fairly recently. When was Van Ramsdonk's paper, Bartek? How long ago?
2009. Yeah.
Right.
5 years.
5 years ago. And since then, people have been thinking about it. This Einstein-Rosen bridge picture is really a special case of it. It says that this geometric connectivity, if and only if there is entanglement. So either you have two disconnected black holes when they're unentangled, or they're kind of sewn together by the entanglement. That idea was really spelled out, not quite in this context, not exactly in this context, by Mark Van Ramsdonk in a really great paper. There's really extremely interesting versions of it now being developed at Stanford, I'm glad to say, by Bartek and by Lampros here. And so these are evolving ideas. They're all connected. And what they're telling us is that the two subjects of quantum mechanics and gravity are not two subjects, that they're joined much, much more thoroughly and much more intricately than anything we imagined. We still haven't gotten to the punchline. We don't know what the punchline to all of this really is. We're seeing fragments of connections, and the connections are such that you get the feeling that someday there is not going to be quantum mechanics and gravity. I don't even think we'll call it quantum gravity. That has two words to it. It'll be gravity. Gravity. One word. One word, some kind of system which just manifests different properties, and that you really can't think of gravity without quantum mechanics, and you can't think of quantum mechanics without gravity. We already see this here, that you can't think of the spatial connectivity of these two regions without thinking about entanglement, and you can't think about entanglement without thinking about spatial connectivity. This is an exceedingly, we are living in a golden age of both quantum mechanics and gravity. There are things happening that are out of the imagination that anybody had 15, 20 years ago when quantum gravity was a complete mystery. It's not so much of a complete mystery anymore, but what is happening is, I don't know how to describe how exciting it is. It's incredibly exciting, and it's being pushed. It's being pushed by a very interesting collection of concepts from different areas. It's being very, very heavily pushed by what is called quantum information theory. Quantum information theory is basically about how information is stored and manipulated and used in quantum mechanical systems as a resource, how entanglement is used as a resource for communication, among other things. So the quantum information people, the quantum computer people, have developed a large number of concepts that are paying off in a totally different framework, in the framework of understanding quantum mechanics and gravity. And in fact, if I'm right about where this is going, in particular this paradox about what it is that accounts for the growth of these things, computer science is coming into it. Concepts from computer science, concepts like complexity. What is complexity? Complexity, I was down in Santa Barbara, and I joked at the beginning of my seminar, I was paraphrasing Douglas MacArthur. I said, old physicists never die. They just go to Santa Fe and talk about complexity. But, right. What is complexity in computer science? Complexity in computer science is a measure of how difficult it is to solve a problem. Solving a problem means two things. It means setting up a computer program to solve the problem and running the computer program. There are two ways that a problem can be very complex. One is if the computer program to solve it has to be very, very long. The size of the shortest computer program that can solve a problem is called algorithmic complexity. But then there's the question of once you've programmed the computer, how long does the computer have to run before it solves a problem? And that's called computational complexity. Computational complexity is something that's interesting for classical computers, but it's wildly more interesting for quantum computers. And that is now beginning to enter into the subject of black holes and quantum gravity, the complexity ideas. So the lesson from all of this is that there is some subject, and we're touching on it, and we're constantly touching on it in deeper and deeper ways, which is the synthesis of the ideas of space-time and gravity on the one hand, and quantum information theory, entanglement, complexity, and so forth on the other. And I would guess in 5 years we will know a lot more. When will we know everything? When will we have a complete theory? Bartek, when will we have a complete theory? You're not telling me. I hope you're going to make the complete theory while you're still at Stanford. Right. But it could be 100 years, it could be 50 years, it could be 10 years, it could be who knows, we don't know. Next time I'll tell you a little bit about quantum complexity and its relationship to the growth of the Einstein-Rosen bridge. As I said, it's the growth which prevents signals from being able to go from one side to the other. And hopefully we do have another candidate to give another series of short lectures. It's Sean Hartnell, who will also talk about gravity and information, but he will be talking about, I believe, the connections between gravity and condensed matter physics, superconductivity, that sort of thing. Very interesting. So we're going to continue, and I'm going to lean on my colleagues till we have everybody telling you what it is that they're interested in. And we'll do it over and over and over again every time physics changes a little bit, every time they change their minds and say, well, I was wrong, let's do something else. We'll create a history of them. Anyway, I hope you're enjoying it. I am.
Thank you.
For more, please visit us at stanford.edu.